All right, ladies and gentlemen, welcome back to another video with Mr. Kenton. We're in topic 6.7 now, and we looked at previously with enthalpies of reaction, and now we're going to look at a way in which we can estimate enthalpies of reaction by looking at what are known as bond enthalpies. Okay, and bond enthalpies, this can be found in section 8.8 in the text. If you think back, this goes back to our unit on chemical bonding. And this is going to pertain to covalent substances, so substances where you've got two nonmetals that are bonded together. And so in 6.7, we're going to be looking at this idea of bond enthalpies. So without further ado, let's go ahead and dive right in. So we introduced, or you might have seen previously that, excuse me, we talked about the strength of bonds, right? And the strength of a bond can essentially be measured by determining how much energy is required to break it, right? And if you think back to our bonding unit, we talked about single bonds were weaker than double bonds, which were weaker than triple bonds. Well, that's because their bond enthalpies are less than, right? And so this term bond enthalpy corresponds to our covalent substances, and it's something that's been tabulated. And so you'll have a reference, you'll have a table or something like that that we can use to look at these bond enthalpies. And again, bond enthalpy is the energy required to break the bond, specifically the energy to break a mole of that bond. Now, for example, we've listed that the bond enthalpy for a chlorine-chlorine single bond, which you'll find in the text as represented by a D, bond enthalpy of a chlorine-chlorine single bond, is measured to be 242 kilojoules per mole. Right? So 242 kilojoules of energy are added to that, and if it's a mole, it's going to break apart the Cl-Cl single bond. Now you can represent this as a chemical reaction of writing the Cl-Cl, that bond, drawing it over to make two chlorines that have one lone electron. All the other electrons are paired up, right? So that's just kind of the generic way to represent covalent bond enthalpy. Now, when you start to look at a table, for example, like what's provided here, this is also in your textbook, it's going to be an average bond enthalpy. Okay, and that's important because essentially what the text is doing and what the table is showing you is these are the average values. If you start to look at individual substances, you might find some deviations in a carbon-hydrogen bond. Maybe in one substance, the carbon-hydrogen bond has a bond enthalpy of 413. Maybe in another one, maybe that energy is slightly higher. Maybe it's slightly lower. So just kind of recognize it's an average. So each individual substance might have its own unique bond enthalpy, but these averages are going to put us in the ballpark to help us estimate the enthalpy of a reaction. Now, bond enthalpies, if you think about it, it's the breaking of a bond. That means that it's going to require energy. So that's why bond enthalpies will always have a positive value when you look at their table. Okay. And again, we've already looked at this. These are averages over many different compounds. And so we would anticipate that if we were to look at them individually in a compound, we get that data. They might not match up with the values perfectly, but they would be at or around that average value that's listed here on the table. And we can see just even this idea of looking at the difference in strength. You got the carbon-carbon single bond at 348 kilojoules per mole, but then you look at a double bond, carbon-carbon 614, and then the triple bond of carbon 839. So we can see that relationship of how shorter bonds, triple bonds, are stronger because they require more energy to break. The other thing that we can note here, and again, I'm drawing back in our previous knowledge, if you start to look at, for example, the hydrogen bonds, so HH, HF, HCl, HBr, and HI, you get this interesting trend. So you look at hydrogen paired up with the halogens, HF 567, HCl 431, HBr 366, and HI 299. There's this kind of steady drop that we're seeing. Well, that should make sense to us because the difference in electronegativity, HF is a very polar molecule. and so it has a higher average bond enthalpy, right? And so as we move down the group, we see that decrease in electronegativity difference, and therefore we see a weakening of that bond enthalpy. So just another thing to kind of tie into things that we've already previously seen, giving us an explanation for why that might be the case. Now, again, we can use bond enthalpy as a way to estimate enthalpy of reaction. Like we said, energy is added to break bonds, and it's released when making bonds. And I'll say that again. Energy is added to break bonds, and energy is released when bonds are made. Okay? And so one way that we can estimate delta H is we can use bond enthalpies of the bonds broken and the bonds formed. Now, that means that you're essentially looking at the enthalpy of the reactants, the bond enthalpy of the reactants, minus the bond enthalpies of the products, right? And so delta H of reaction is going to equal the sum of the bond enthalpies of the bonds broken, aka bonds broken. This is going to tell us reactants, minus the sum of the bond enthalpies of the bonds formed, aka products, right? And I like to think of it in terms of reactants and products, because remember, bond enthalpies are always looking at the breaking of the bonds. And so that's why I like to use the terminology of the bond enthalpies of the reactants minus the bond enthalpies of the products, because it helps us with understanding that the bond enthalpy needs to be a positive value. Okay, so if we take a look at an example, we've got methane plus chlorine makes chloromethane and hydrogen chloride gas. Now, if you were to draw this all out, what we would be able to identify is that we've got a carbon-hydrogen bond and a chlorine-chlorine bond that are being broken, and then you've got a carbon-chlorine bond and an HCl bond that are being formed. So what we would do, we'd take, again, it would be the sum of the bond enthalpies of the reactants minus the sum of the bond enthalpies of the products. So then what you're left with, the bond enthalpies of your reactants would be the carbon-hydrogen bond and the chlorine-chlorine bond. And then your products would be the bond enthalpies of the carbon-chlorine bond and the bond enthalpy of a hydrogen-chlorine bond. So then you would look at your average bond enthalpy data in the table. You got one CH bond, that's 413 kilojoules. You've got a chlorine-chlorine bond, which is at 242. Those would be the bond enthalpies of your reactants. You'd combine those two. And then you've got your bond enthalpies of your products. So carbon-chlorine is at 328 kilojoules, and hydrogen-chlorine is at 431 kilojoules. You combine your terms, so your reactants have a total energy of 655. Products, total energy of 759. Take the difference, and so then the estimated delta H for this reaction would be negative 104 kilojoules. So overall, we would anticipate, based on our bond enthalpies, that this reaction is exothermic, because it has a negative delta H value. Okay, and again, bond enthalpy is a way for us to estimate delta H of reaction. Not the best way, but it is a way that we can use to estimate enthalpy of reaction values. All right, that, ladies and gentlemen, is bond enthalpy. I hope this video was insightful. If you have any questions, you know where to find me. You can email me. You can post your questions on Google Classroom. Just let me know. Thank you so much. Hope this was helpful. I'll see you guys again soon. Take care.